Okay. Hello, everybody. So I'm Alexis Bouquet. I'm going to tell you about my past research experience and my current skills. So I have a bit of an unorthodox orthodox background because I started as an engineer in the private sector in aircraft handling quality simulation. So I was working for a subcontractor who sent me to the design office of Airbus. So part of my work was to run simulations of maneuvers and see if we could reconcile the simulator with the reality of a flight test. So during this period, that's when I noticed that I was way more interested by the research aspect of the work, especially when I was told there is something unexplained in the simulator, we have to find an explanation. So I went back to school and I did a master's degree in astrophysics in the University Paul Sabatier of Toulouse. And during my master's degree internship, my first research experience was the development of a Python code to simulate the detection of meteors from orbit. So I already had an interest in small bodies because technically meteors are caused by very small bodies. But I started really working on icy bodies and outer planet satellites during my PhD. So I did my PhD in the joint program between the University of Texas at San Antonio and the Southwest Research Institute between 2014 and 2018. So my work was on processes affecting volatiles coming from the icy moon of the solar system with a heavy focus on Enceladus because my advisor was Hunter Waite, so the PI of the mass spectrometer on Cassini. So I was working mostly on the data regarding Enceladus and simulations attached to Enceladus. That include numerical modeling of clavite formation and how it could trap the volatiles that INMS was seeing, and therefore how it would affect their abundances. And the endogenic radiolysis inside Enceladus, so that's when radioactive materials in the rocky core interact with water and could produce hydrogen. Hydrogen had been detected by INMS, but we were still struggling to point out where it was coming from. I also worked on how it could be produced inside the instruments by impact of icy grains on the titanium. And so all of that work contributed to identify and quantify the presence of endogenic hydrogen coming from the ocean of Enceladus, and that was most likely produced by hydrothermal reactions. So that was one of contribution in a massive team, but that got me really interested in continuing for the search for habitable conditions in icy moons of the solar system. So my skills involved were mostly in Python programming, modeling, assorted with a little bit of data interpretation and mass spectrometry. And of course, the general icy moon context. So next slide, please. So I'm currently in my first postdoc after my PhD. It's a postdoc on a CNES fellowship. So CNES is a French space agency. And it's a more experimental postdoc because it's about the irradiation of astrophysical ice analogs. So we're proceeding to the irradiation of water, methanol, ammonia ice in the Ganil facility. So it is a big facility with a powerful ion beam. And it has a pretty rare ability to produce a beam of sulfur, which can be used to represent the sulfur from the solar wind, but also the sulfur that hits the surface of the moons of Jupiter. So I've worked on the monitoring by FTIR spectroscopy. The workflow included the analysis of organic residues, and we found that we were forming a large variety of organosulfur compounds by implantation. Our experiments so far are directly applicable to KBOs, but we're going to make a second series of experiments that I designed, potentially applicable to Jovian satellites. So the skills involved working on IR spectra and working with UHV systems and ion beams and designing the second set of experiments. Next slide. So I'm leaving you with my contact information. My current postdoc is scheduled to finish by September 30th, but it could be prolonged because of these little events going on right now. And my main center of interest stays on the surface processes of the icy moons of the solar system. And I would be mostly interested in developing experimental work. Thank you.
Okay. Thank you, Alexis. Okay, Ellen.
All right, can you hear me?
Yes, yes, we can. So when you're ready, go ahead.
All right. Hello, everyone. Thank you for joining today and taking time out of your schedules to watch these presentations. My name is Ellen Czaplinski, and I got my bachelor's degree in planetary science from Purdue University. And this is where I got my start in planetary science research. I did a project looking at Mars dunes and the slip face features on them, and I mapped these throughout the surface and kind of classified them based on the slip face type and tried to determine their origin. From this project, it was a great introduction to GIS and remote sensing techniques. I got a great introduction to geomorphology as well as spacecraft image interpretation. After I finished my degree at Purdue, I was accepted to the University of Arkansas Center for Space and Planetary Sciences, where I started my PhD. I'm currently a fourth-year PhD student, and I'm hoping to finish by this time next year, and so I'll be applying to postdocs and looking for postdocs in the next year. So at Arkansas, I use a surface simulation chamber to study evaporites on Titan and try to learn more about the composition and dynamics of Titan's lakes. So you can see a schematic of the Titan chamber I work with on the right. I won't go into a whole lot of detail here, but basically what this chamber allows us to do is take samples that are liquid or gas at room temperature, introduce them into a condenser in the center of the chamber, and then after we cool the chamber down to Titan temperatures, I can deposit these as a liquid or a solid into the bottom of the chamber where I study them with FTIR spectroscopy. So in my PhD research, I've learned a lot about laboratory techniques. I use FTIR and Raman spectroscopy, as well as a lot of organic chemistry and chamber engineering, because as you can see in that central upper image, it's a pretty complicated piece of machinery. Next slide, please. So now I'll get into a little bit more detail of my Titan research. So in the upper two images, you're looking at a top-down view of our sample dish in the chamber. And so in this example, I have a mixture of acetylene and benzene on the sample dish. And on the image on the left, it's a little bit warmer temperatures, and you can see it's just kind of like a, almost like a snowy texture. And then on the right, when we cool down the sample to closer to Titan temperatures, you can see there's significant changes to that sample, and you can see a lot more structure in that. So we can study our samples visually as well as using FTIR spectroscopy. So as you can see in that bottom image on the left, this is showing a graph of a methane and ethylene evaporite experiment. So here methane is the liquid, ethylene is the solid, and if we focus on that spectrum at the bottom, you can see that methane triplet around 1.7 microns, but as we move up in the graph, you can see that methane disappears. And that's because methane is evaporating and leaving behind an ethylene evaporite in this type of experiment. So with these experiments, I can measure evaporation rates, saturation values, determine the solubility of my samples, as well as compare my spectra to spectral models. So with this, these types of experiments, I actually published my first author paper in 2019. And I'm continuing to do these types of experiments over the next year. Next slide, please. So in addition to my Titan research, I'm also interested in the South Pole of the Moon in reference to lunar exploration. So I did an internship at the LPI in 2018, where me and my fellow interns created a geologic map of the Schrödinger Basin, which is out the South Pole of the Moon, and it has a lot of interesting geology in the peak ring. So we were able to map this, and we also planned several landing sites and rover traverses from this. Additionally, I was the Mars Desert Research Station crew geologist in 2018, where I went on several field excursions throughout a 2-week simulation mission in the Utah desert. And I collected several clay samples, as well as using a portable spectrometer to analyze these. Additionally, I'm really interested in spacecraft missions, which is why I applied to and was accepted to the JPL Planetary Science Summer Seminar, where me and my fellow interns planned a mission to study an interstellar object. Thank you for listening. If you're interested in any of my research or want to know more about what I do, I encourage you to contact me from the information on the slides, or we could start a breakout session. Thank you.
All right, thank you, Ellen. So at this point, if anybody who's online watching our presentations this morning, if you would like to speak with either Alexi or Ellen at this point, or after everybody's done, just send a message in the chat box, just letting us know which presenter you want to speak with, and then we will be happy to put you in your own breakout room. All right, up next we have Adeene.
Great, hi. Can you hear me okay?
Yes, so whenever you're ready.
Awesome. Hi there. I'm Nadine Denton, a fourth-year PhD student in planetary science at Purdue University. And in my work, I'm interested in using 3 fundamental geologic processes to understand the evolution of both rocky and icy bodies in our solar system. Together, impact cratering tectonism and surface processes like mass wasting and volcanism combine to produce the incredibly complex geology that we observe from spacecraft, which only hints at what's going on beneath the surface. And as a numerical modeler who's passionate about grounding my results in observational geology, for my thesis, I've developed an approach that integrates each of these geologic processes using several different tools so that we can peel back the lids of these worlds and understand how they evolved. Meaning, I use a combination of impact modeling, finite element modeling, and observational work to simulate the evolution of massive impact basins from their formation through to the present day. And right now, I'm trying to understand what's going on beneath the surface of Pluto, everyone's favorite exoplanet. This image in the center is Pluto taken by New Horizons. And what I'm interested in is the bright white elliptical feature in the center. This is Sputnik Planitia, a massive impact basin bigger than the American state of Alaska that's covered in kilometers of convecting nitrogen ice. And there's so much we don't understand about Pluto, including whether it has an ocean beneath its icy crust, how thick its ice shell is, and what its core is made out of. And while we may not be going back to Pluto anytime soon, if we get inventive with the data that we have, we can get closer to answering these questions. Sputnik Planitia is believed to be a massive impact basin because of its elliptical shape, and also the fact that it's a giant hole in the ground centered near the Pluto-Charon tidal axis. And because of this, the disruption induced by impact can act as a probe for us to examine the subsurface. We can use the stress waves that propagate through Pluto during and after impact, as well as how the resulting basin relaxes over geologic time, to analyze the dwarf planet's interior structure. What I do is simulate the formation of Sputnik Planitia from impact using the ice-sail shock physics code, where I throw a giant ice ball at Pluto and watch what happens. And what I'm showing on the right is an image from one of these simulations that illustrates how the massive size of Sputnik Planitia causes its formation to affect Pluto on a global scale. The ongoing formation of Sputnik Planitia is at the top of the image, and the basin's antipode is down at the bottom. And what we're interested in are the processes going on in the interior. Material is colored according to target velocity to show you how transmission of seismic waves released from impact varies in both the core and the ice shell. These variations in material properties are what determines how these waves are eventually focused to the antipode, where they actually produce surface deformation that's been observed by New Horizons. And by using observational data from Pluto's far side to bracket my model results, I can determine what kind of internal structure is necessary to match them. And our results indicate that Pluto needs to have both a thick ocean and an at least partially hydrated core. This finding is something that we can learn just from seismic waves released during impact, but there's actually so much more we can learn about Pluto from Sputnik Planitia that depends on how the basin evolves in the ensuing billions of years. The end result from my shock physics code is a basin that looks kind of like Sputnik Planitia today in size and shape. And to go from the formation of Sputnik Planitia through to the present day, I use a finite element code to take that basin that I've made and let it cool down and relax, as well as load it with the nitrogen that we see on the surface to reproduce the basin in its contemporary form. In using this technique and testing different models for the thermal structure of the ice shell and underlying ocean thickness, we can actually get much, much closer to understanding Pluto's thermal and mechanical structure with the little surface data that we have. In addition to my primary work on Sputnik Planitia, I'm also doing several other projects, including pairing impact simulations with new mapping work for Bernie, Pluto's moldering basin that we can actually see northwest of Sputnik Planitia to probe the thermal structure of Pluto's ice shell in more detail. I'm also revisiting the possibility that the seismic waves released by the formation of Odysseus, the 400-kilometer basin on Saturn's moon Tethys, might produce significant surface shear stresses that form the massive Ithaca chasma, and I'm looking at improving implementation of critical impact cratering mechanisms in ICEL itself, including things like acoustic fluidization. Together, my projects have developed my skills in observational analysis and data processing, as well as numerical modeling. And after I graduate in either summer or fall 2021, I hope to continue using my skills to look at basin evolution across the solar system and come closer to unraveling planetary history. Thank you, and I look forward to talking with any of you further about my work, either here or contact me elsewhere.
Thank you, Adeene. So again, if anybody wants to speak with Adeene or Alexis or Ellen, our previous presenters, just send a message through the chat box and we will place you, let us know who you want to speak with, and we'll place you both in a breakout room. Okay, our next presenter.
Hi there, my name is Rachael Hamp and I am a third-year PhD student at the Open University. I am a member of the Astrobiology Research Group, where I look at the geochemistry of the icy moon Enceladus. So prior to this, I come from a pure chemistry background, where I've previously specialized in computational atmospheric chemistry and analytical chemistry. My PhD is looking at carbon cycling in the subsurface environment of Enceladus. So Enceladus is known to be one of the most likely places that we can find life in our solar system outside of Earth. This is due to the fact there is a global subsurface ocean, bioessential elements, and areas of hydrothermal activity on the South Polar region. So from these bioessential elements, carbon is one of the key ones. Carbon is fundamental to life as we currently understand it. So through my PhD work, I have studied the interaction of the silicate interior of Enceladus and the subsurface ocean fluid. And through this work, I hope to piece together clues about the chemical and the physical environment in the subsurface ocean to answer further questions about Enceladus's potential habitability. Next slide, please. So my project has been split into three main sections. So the first thing that I did was I designed a silicate simulant to represent the silicate interior of Enceladus. This simulant has been designed based upon the average CI carbonaceous chondrite chemistry. And here modifications have been made based upon observations from the Cassini spacecraft to make it more applicable to Enceladus. If you'd like to know specifics about this simulant, it contains 15 minerals and various organics, but for the exact chemical composition, please look at my 2019 LPSC abstract and poster. The second part of my PhD was looking at thermochemical modeling of the rock interactions with the subsurface ocean interactions to try and deduce a hypothetical chemistry for a modern day subsurface ocean. Through this work, I ran two models. The first one interacted the silicate chemistry that was designed in step 1 with a fluid for the subsurface ocean that was essentially just pure water with very small trace amounts of sodium chloride. The second model was that silicon chemistry again, but this time reacting with a cometary ice fluid. Now, this was to test the hypothesis that the ice on the exterior of Enceladus could once have originated from a cometary source. The results from both of these models at different temperatures and pressures were compared to the Cassini data, which has allowed me to deduce a hypothetical composition for a modern day subsurface ocean on Enceladus. Other key results that my modeling results have shown is that I've managed to deduce a hypothetical pathway for the formation of hydrocarbons in the subsurface environment of Enceladus. We've also managed to determine a hypothetical formation of the silicon nanoparticles that have been detected in the plumes and the pathway that these are most likely happening. And then the third and final part of my PhD is currently in progress. And this is where I'm carrying out laboratory-based experiments and trying in the lab to recreate the subsurface environment in a high-pressure reactor vessel. So here I'm using that simulant that was designed in stage 1, and I'm using the model outputs from stage 2 and recreating the rock-water interface. Through studying the changes in the mineralogy of the silicate and the changes in the fluid, hopefully here we'll be able to piece together the key reactions that are happening in the subsurface environment and get a better understanding of the chemical and the physical conditions, and hopefully answer further questions about Enceladus's habitability. Next slide, please. So if you have any further questions about any of my work, I'll be happy to talk to you afterwards, or please just drop me an email and I'll be happy to discuss anything else. Thank you.
Okay, thank you, Rachel. And I will move on to our next presenter.
Hello, everyone. I'm Ishan. I am a third-year graduate student at the Cornell's Department of Astronomy and the Carl Sagan Institute, which is an interdisciplinary astrobiology research institute hosted within the Department of Astronomy at Cornell. My advisors are Nicole Lewis and Jonathan Lunine, who bring cross-disciplinary expertise in exoplanet science and solar system science, respectively. So my broad interest is planetary spectroscopic data analysis, or retrievals, which basically means extracting compositional and physical properties of planetary surfaces or atmospheres by analyzing its spectra with various statistical techniques. And if I had to get into specifics, I'm interested in various things. Firstly, I'm interested in icy moons of our solar system that harbor subsurface ocean, like Europa and Enceladus. Specifically, I'm interested in improving our knowledge of their surface composition through spectroscopy and what it can tell us about the habitability of the subsurface ocean. So how do we link the composition that we see on the surface to what's going on inside these subsurface oceans? Secondly, I'm interested in spectroscopy of exoplanets, as it involves application of advanced statistical techniques for analyzing spectroscopic data. And actually, my training in data analysis comes from working with exoplanet transmission spectrum, because my primary advisor has expertise in exoplanet atmospheric characterization. And so since exoplanet people specialize in working with low SNR data, their methods and skills are transferable to the problem of finding weak signals of trace compounds like organics on the surface of icy moons in our solar system. So that's where this collaboration comes in. And for spectroscopic data analysis in general, I'm interested in application of machine learning techniques that are becoming increasingly popular. And again, exoplanet science is at the forefront of it, and there's a lot that can be borrowed into the application of to icy satellite spectroscopy. And finally, my research involves a lot of programming, and hence I have developed an interest in open source research, software development, and open source research in general. And currently I'm working on publishing my own Bayesian data analysis package written in Python for solar system reflectance spectroscopy. So I want to quickly highlight the projects I've been part of and I'm working on right now. So firstly, with my primary advisor, Nicole Lewis, again, who is an expert in exoplanet atmospheric characterization, I analyze the transmission spectrum of hot Jupiter HAT P41b, collected by Hubble Space Telescope that went from the near UV to near IR. And our goal was to find absorption signature of disequilibrium species in their atmospheres. So this was my first big collaborative project, and our paper is currently under review. My second project, which was my first lead project as part of my thesis, which I just wrapped up, is concerns Europa, which is going to be the subject of my thesis, as I said. And I led this project with both my advisors and 4 other collaborators, and I performed a thorough compositional analysis of select spectra of Europa that were collected by Juno mission last year. And these are they were published last year. That was collected over 2016 and 2018. But these are high-quality spectra that span 2 to 5 microns, and we did a simple Bayesian analysis to find the evidence of crystalline and amorphous water ice, and also constrain their composition and abundance. Their abundance and the average grain sizes. And I have been, since my main research group is heavily involved in observations, I've also been part of 4 phase 1 Hubble proposals for exoplanet transit spectroscopy research, including 3 this year and 1 that was unsuccessful last year. So I've listed on the skills that I've gained through all my work so far, and it spans data analysis, working with Hubble data and Juno-Geron data, then a lot of Python software development and collaborative research in general. Next slide, please. So my work in the coming years, at least while I'm in grad school, will concern my primary thesis topic of providing quantitative constraints on Europa surface composition. So the idea is that we systematically test for the presence of different species for which we have the lab optical constants, and like we model synthetic spectra using a radiative transfer model and try to fit the spectra and systematically find evidence for the different species. And so as part of this, I plan to do a lot of things. First of all, I want to develop a code for numerical model for planetary surface spectroscopy that can be used in a Bayesian framework. So currently I'm using a bidirectional reflectance model that is called half-case model. It's a very popular model, but it has its shortcoming, especially in very absorbing media. So I want to see if there are other alternatives and a computationally fast alternatives, because I'm doing a simulation. In Bayesian inference involves simulating millions of spectra, so you are computationally limited. So that is something that I'm interested in, finding a computationally fast but accurate model. Then I also want to do lab work to derive cryogenic optical constants of non-waterized species on Europa, because any species that you want to include in your analysis, you need to have their optical constants or refractive indices. And unfortunately, there is a severe dearth of this data. So I will be collaborating with people in Ocean World Lab at JPL. But if anyone has already got this data or is interested in collaborating with it for this work, please let me know. Then finally, I am interested in doing a lab work to test my analysis framework. So I want to collect reflectance data of icy surface regolith in labs, and like design experiments so that I can test my analysis framework and find exactly what the shortcomings of the model I'm using in my framework is, the statistical technique I'm using, and so on. Like we can also study the effect of different parameters we are using in our model in a controlled way. So that is something I'm very interested in doing. So if anyone has a lab which can collect these measurements and of cold samples, then please let me know, and we can definitely collaborate or just talk. Finally, I'm interested, because of my involvement in observation proposals, I'm really interested in getting involved in solar system based observations and write proposals for that. So with a noise simulator and like with the reflectance model that I'm using, I can generate synthetic spectra, and if we combine it with a noise simulator, we can get synthetic.
Ishan, I'm sorry, but I'm gonna need you to wrap up as soon as you can.
Oh, I didn't see your sign. I'm sorry. Yeah, sorry. My analysis framework can help us better understand what species can we detect if we are just planning to observe an object, and what kind of features we can detect. We can provide quantitative constraints on that. So that can be a useful pre-analysis that can be included in a proposal. So if anyone is interested in talking to me and they think that I can contribute to their proposals, please let me know. So yeah, thank you all for listening. I apologize for going over the time and not seeing the sign by Andrew, but my contact information is on this slide, and I hope to talk to you. Bye-bye. Thanks.
Great. No problem. Thank you, Ishan. All right. Okay. Ihor.
Okay. Hello, my name is Ihor Kirillenko. I'm a junior research scientist at the Institute of Astronomy of Kharkiv National University, and currently my work consists of developing methods and programs for asteroid pair search, as well as seeking new asteroid pairs. So it is well known that a lot of asteroids are included in families of pairs. The first slide illustrates the process of how a pair is created. One way it is because other asteroids zoom in and colliding, causing disruption into a pair, or by a mechanism called York effect that is marked by circling arrows. and is essentially solar-like pressure which can slowly speed up the rotation of an asteroid, later causing the breakup by the centrifugal forces. As a result, we have to separate asteroids with small initial relative distances and velocities, but as the time progresses, as timeline shows at the bottom, due to perturbations from other planets, their orbits drift apart as shown by dashed lines. And the only thing we possess is the present asteroid orbits among thousands of others. So how to discover these pairs and to uncover their dynamical history? Firstly, to identify such asteroids as a potential pair, I use hierarchical clustering method that consists of calculating the distance between asteroids in a phase space of oscillating orbital elements. And to confirm or invalidate those potential pairs, use a backtrack integration technique, or if to put simply, modeling backward. For backtrack integration, we adopt a rebound package that is available for Python and C programming languages, and made several coding extensions to suit our needs. Using this package, we model our solar system with asteroids studied into the past to find possible moment of their disruption, as it's shown by the red arrow to the left. And the plot on the background shows pairs parameters, which are relative velocity colored orange and the distance between them colored blue. The cusp corresponds to the close encounter, which is a disruption moment due to the Ihor effect. Unfortunately, none of the important parameters is known with perfect accuracy. That is why we can't ideally recreate the system to get a precise answer. And to mitigate this, we reproduce possible system states simulating a large amount of asteroids with varying parameters like positions, velocities, or masses. And the histogram on the upper right shows the most possible disruption times. Next slide, please. To prove the working efficiency for our pipeline, we did a blind test. For this purpose, we took 20 of rediscovered during our survey pairs with already determined ages and recalculated them. The x-axis on the plot shows known ages for these pairs, and y-axis shows recalculated by us. So red lines are error bars, and for some asteroids they are too small to be seen. It's okay. So there's pretty good agreement of our results and known ones. So it is safe to say that our pipeline for discovering and confirming pairs works correctly. Using this, we surveyed in a main asteroid belt and got nearly 500 pair candidates. Their processing continues right now, but we already found a couple of new pairs, and hopefully we will obtain more at the end of our investigation. So as a result, we got a working pairs search pipeline, made a survey of inner main asteroid belt, and found new asteroid pairs. And we are planning to implement Yarkovsky effect, which is overall an effect of solar radiation causing drift of semi-major axis of an asteroid, and a smart searching algorithm for asteroid clones to get encounter times faster, and to study different populations like near-Earth asteroids, which have quite chaotic behavior, the whole main asteroid belt, and maybe trans-Neptunian objects. Next slide, please. So if you have any further questions, suggestions, or anything else, please feel free to contact me by email, Telegram, or WhatsApp, or join me in a breakout room. So thank you for your attention.
Okay. Thank you, Ihor. Up next, Ying.
Oh, hi. So, hi everyone. I'm Liao from Taiwan, and now I work as a joint postdoc in National Central University and Origin Space, which is a very young startup aiming at developing CubeSat missions for asteroid mining and other commercial applications for CubeSats. So I started to get involved in the field of planetary science since my master in National University in Taiwan. And then I did my PhD in University of Bern in Switzerland. And my research was related to ESA's Rosetta mission. And after that, I did a postdoc in Macau University of Science and Technology, in which I started to develop another research interest in the space mission design. So now my research interests include solar system small bodies, numerical modeling, and the mission design. Next, please. Yeah, so my PhD project mainly involves in the reproduction and the investigation of the parameter space of the cometary outgassing using the DSMC approach. So DSMC means direct simulation Monte Carlo, and it uses probabilistic simulation, which is Monte Carlo, to solve the Boltzmann equation for rarefied gas flows. So it's extremely useful in the modeling of the outgassing process of small bodies and also the planetary moons such as Enceladus and Europa. So the whole simulation work usually begins with a shape model of the nucleus. So I will get the nucleus, the shape model of like comet 67P Churyumov-Gerasimenko, which is the target of Rosetta, and I will turn it into a numerical grid made of the tetrahedral cells, and then I will apply the insolation model, which is the where is the shadow area and where is the illuminated area, and then the energy balance equation, and then it will turn into a thermal. We call this a thermal model, but which is just basically the temperature and the initial gas number density distributions on the surface of the nucleus. And then I will put all these parameters in the code, in the DSMC code, which is called PDSC++. And then it's a long, it usually takes like 1 to 2 days of computation, and then I will get the gas flow result as in like temperatures, number densities, velocities, and so on. And then I will take into these data and analyze it. Yeah, so to sum up, I have identified the effectiveness of a series of models and the gas dynamic variables of the cometary outgassing. And the results are extremely useful for interpreting the data acquired by Rosetta. And for more details, you are very welcome to take a look at my papers in 2016 and 2018. Next, please. Yeah, so the topic I'm working on right now is the design and realization of our CubeSat mission phase, potentially hazardous asteroid CubeSat exploration. So last year, my colleagues and I, we proposed a mission to investigate the asteroid Apophis during its close approach in 2029. So Apophis will come very close to Earth, which is about the distance, almost the distance of the altitude of GEO satellites in 2029. So such a close encounter of an asteroid will open a window of possible rendezvous missions for spacecraft only by very low velocity impulse, which is in particular beneficial to CubeSats as their propulsion system is usually very limited. And we believe this is a great opportunity for both scientific explorations of a near-Earth asteroid and the practice of planetary defense using CubeSats. So all of our subsystems are primarily based on the cost product with very high level of TRL. And the total cost we estimate is about $800,000 US. And we're very pleased that our idea got the first place. It's recognized in the CubeSat mission design contest held by our national space organization in Taiwan. So that's all. Thank you very much for listening. And I would like to thank Andy and other hosts as well for their huge effort in organizing this great online event. So hope you all stay comfortable and healthy, and welcome to reach me at my email or my LinkedIn. Thank you.
Very good. Okay, thank you, Ying. Okay, our next presenter. Oh, Gabriel, there we are. Trying to, there, okay, there's your, all right. Okay, whenever you're ready. You're still muted.
Hi, everyone. My name is Gabriel Muñiz-Negrón. I'm an undergraduate electrical engineering student at the University of Puerto Rico at Mayagüez. and I'm currently on my 5th year of a 5-year program specializing in radio frequency systems and microwave remote sensing. So jumping right into my research experience, right here you can see on the left an image of the Pride radar, in this case the printed circuit board. I actually worked this project with the LPI. This is my most encompassing project since I worked on the microwave side and the antenna side. And I worked on the design and fabrication of the microwave circuitry behind the radar and the antennas themselves. On the right, you can see an RF harvesting pacemaker proof of concept. This was my engineering capstone project. I worked on the power calculations and the antenna design for the proof of concept and an eventual prototype. In these 2 projects, I applied existing and acquired new skills in the area of microwave engineering, including the study, design, simulation, and fabrication of the microwave circuits, as well as some basic antenna engineering, including the design, simulation, and fabrication of these antennas at 24 and 2.4 gigahertz, respectively. Next slide, please. Okay, so here you can see on the left, this is a slot antenna array implemented with waveguide technology. I implemented existing antenna designs with the use of the relatively modern technology of waveguides. This proved to be a great alternative to other technologies, such as substrate integrated waveguides, since their lack of the electric material allows for spaceborne applications. So in this case, we're just using these metal pins as perfect magnetic conductors to keep all the electric fields and magnetic fields inside of resonant cavities. On the right, you can see my current project. This is a wideband Puma array antenna. I'm currently studying the viability of substituting the shorting poles of the existing structure with printed metasurfaces to achieve the same behavior while reducing fabrication complexity and overall size. This antenna on the right operates from 4 gigahertz all the way up to 20 gigahertz. So it's a really broadband antenna. In these 2 cases, I have had to apply more advanced antenna engineering techniques. Since these structures are way more complicated than the last 2, I developed Python scripts to generate these geometries shown below and make the most out of my computing resources. On the programming side of things, I also have experience with other programming languages, including MATLAB, C language, and TI's MSP 430 assembly language. I also have experience in the use of CAD software for antenna and microwave engineering, including ANSYS Electronics Desktop, which uses the finite element method, and Keysight Advanced Design System. Next slide, please. My main area of interest, as you can see, is antennas for communication and remote sensing, and microwave remote sensing. I'm especially interested in seeing how we can use existing communication and remote sensing equipment beyond their intended use to reduce waste and cost while improving resource availability. I'm also interested in how we can apply this in planetary defense and scientific surveying. Near bodies present an interesting challenge because we have all these satellites surrounding the planet, and we have weather radars, which we could potentially use to see what's coming into Earth and what's surrounding us. But right now, we're not making the most out of what we already have. In essence, that's exactly what I want to answer. How can we make the most of what all these tools we already have with minimal improvements? After graduating in fall 2020, I look forward to continue my studies with a PhD in electrical engineering, specializing in remote sensing and communication systems. You can see here, these are my 2 email addresses. You can reach out if you want to talk about my research or in a separate breakout room. Thanks.